this episode, we're going to connect three networking components that can either make automation feel effortless or make it feel like you're chasing invisible problems: routers, load balancers, and firewalls. For brand new learners, the challenge is that these components often live in the background, doing their jobs quietly until one small misalignment causes an outage or a puzzling failure. Automation puts extra pressure on them because automation tends to create and change things quickly, and it expects the network to respond predictably every time. Routers determine where traffic can go and how it gets there. Load balancers decide how traffic is distributed across multiple service instances, and firewalls decide what traffic is allowed or denied. If these three elements are configured with clear intent and consistent rules, automation becomes more reliable because new workloads can come online and immediately participate in normal traffic patterns. If they are configured inconsistently, automation can succeed in deploying resources while the environment still fails operationally because traffic can't reach the right place or is blocked at a critical boundary. The goal is to understand how to configure them so that change at scale remains safe, observable, and recoverable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The most helpful way to understand routers in an automation-friendly environment is to see them as the decision point that turns a network boundary into a usable system. A router connects segments and chooses the next hop for traffic that needs to leave a local area, which is how subnets and zones become part of a larger environment rather than isolated islands. In a reliable automated environment, routing decisions should be stable, meaning the same type of workload in the same type of subnet should reach its dependencies through the same intended paths. That stability matters because automation often assumes that if a dependency is allowed by policy, it is also reachable by route. Beginners sometimes treat routing and security controls as separate, but operationally they're linked because a firewall rule that allows traffic is meaningless if the traffic can't find a route, and a route that exists is risky if the firewall is too permissive. A well-configured router setup supports clarity by making it easy to predict which paths exist and why they exist. When you can explain the routing intent in plain language, you've usually built something that automation can rely on without hidden surprises. Routers become especially important when you consider that automation frequently introduces new endpoints into the network, and those endpoints need to be reachable in the same way as existing ones. If your routing is full of special cases that were added over time, a new workload might land in a subnet where routes look similar but behave differently, causing a deployment that appears healthy but can't communicate properly. This is one reason reliable automation favors consistent subnet patterns and consistent route distribution, so that new resources inherit the same connectivity profile as old resources of the same role. Another key idea is that routing changes can have broad impact because they influence traffic flows for many systems, not just the one you're working on. That's why routing should be treated as critical infrastructure and changed deliberately, because a single routing misstep can isolate monitoring, break updates, or disconnect control plane dependencies. Automation-friendly routing is less about cleverness and more about repeatable patterns that are easy to validate and easy to roll back. The outcome you want is that routing behaves like a stable platform feature rather than like an unpredictable puzzle. Load balancers are the next piece because they sit at the point where clients meet services, and they often become the primary interface that automation-driven deployments must satisfy. A load balancer presents a stable entry point and distributes traffic across multiple instances of a service, which helps with scalability and availability. For automation, the value is that you can replace or add service instances without forcing clients to change where they connect, because the load balancer keeps the front door stable. The risk is that load balancers have their own rules and health expectations, and if those rules don't align with how your services behave during startup and change, automation can create fragile deployments. Beginners often think a load balancer is simply a traffic splitter, but operationally it is also a gatekeeper that decides which instances are allowed to receive traffic based on health checks and policies. If a service instance takes time to initialize, or if it only becomes truly ready after some internal dependency is connected, the load balancer must be configured to recognize readiness correctly. When readiness and health are misaligned, automation can deploy perfectly and still create an outage because traffic is sent to instances that aren't actually prepared to handle it. To support reliable automation, load balancer behavior must be predictable during scaling events and during replacements, because those are the moments automation triggers most often. When a new instance is introduced, it should be allowed to warm up before it receives production traffic, and when an instance is removed, it should be drained gracefully so in-flight requests can complete. Those ideas can be understood without tool-specific detail because they're about safe transitions rather than specific settings. If your load balancer treats any responsive instance as healthy immediately, it may route traffic too early, leading to intermittent failures that look like application bugs. If it removes instances abruptly, it can cut off active sessions and create errors that users experience as sudden drops. Automation-friendly configuration recognizes that load balancers are part of the deployment lifecycle, not just the steady-state traffic flow. When you design load balancing to support staged readiness and graceful removal, you make automated rollouts safer and you reduce the chance that a routine scaling action becomes an incident. Firewalls are the third component, and they are often the most emotionally charged because they are associated with security and blocking, but they are also essential to reliability when configured thoughtfully. A firewall enforces rules about what traffic is allowed to flow between zones, subnets, and services, and those rules should reflect operational intent. Beginners sometimes see firewalls as obstacles because they cause connections to fail, but in reality, firewalls are the reason your network can be segmented safely at scale. The key to avoiding outages is to make firewall policy explicit and aligned with dependency paths so that required flows are allowed and only required flows are allowed. Automation complicates firewall management because automated systems frequently need to reach identity services, logging, time services, update endpoints, and internal control plane components, and those dependencies can be easy to forget. If you lock down too aggressively without understanding dependencies, deployments can fail mid-run or services can come up but behave incorrectly because they can't reach what they need. Automation-friendly firewall configuration is therefore not about being permissive. It's about being precise and consistent. A major beginner misunderstanding is assuming that if a service is internal, it doesn't need carefully managed firewall rules, when internal networks can still have strong segmentation. In fact, internal segmentation is often more important because most modern incidents involve lateral movement after an initial foothold. Firewalls help reduce that lateral movement by ensuring that a compromised workload can't simply talk to everything. At the same time, reliable automation requires that the workload can talk to what it is legitimately supposed to talk to, which means firewall rules must reflect reality rather than assumptions. The safe practice is to treat firewall policy as part of the workload design, meaning each workload role has a known set of allowed inbound and outbound flows. When those flows are consistent across environments, automation becomes predictable because a deployment that succeeds in testing is less likely to fail in production due to unseen firewall differences. Consistency doesn't mean identical for every environment, but it does mean the same logic and intent applies. When you can describe a workload's required flows clearly, firewall changes become controlled rather than reactive. Routers, load balancers, and firewalls also interact, and reliable automation depends on those interactions being coherent rather than contradictory. A route might send traffic through a certain path, but a firewall might block that path, producing a failure that looks like a routing problem even though it's a policy issue. A load balancer might front a service and perform health checks, but firewall rules might accidentally block those health checks, causing the load balancer to mark healthy instances as unhealthy. A router might connect segments, but if routing tables are asymmetric, traffic might go out one way and replies might return another way, and a firewall that expects symmetry might drop the traffic. These are not edge cases. They're common sources of intermittent failures that are painful to debug because each component is individually working while the system as a whole is not. The automation-friendly approach is to configure these components with a shared view of intent. Routes define possible paths, firewalls define allowed flows on those paths, and load balancers define how services are presented and how instances are admitted. When the intent is consistent, failures are easier to diagnose because you can reason about what should happen. Another crucial idea for beginners is that automation changes timing, and timing affects how these components behave under load and during transitions. When automation scales a service quickly, routers and firewalls may see sudden bursts of new connections, and if there are implicit limits or rate controls, you might hit them unexpectedly. Load balancers might see rapid instance churn, and if health checks are too aggressive or too slow, they might behave in surprising ways. A reliable automated environment anticipates that bursts can happen and configures boundaries and checks to handle them gracefully. This doesn't mean turning everything up to maximum. It means selecting behaviors that fail safely rather than catastrophically. For example, if a health check fails temporarily during startup, the load balancer should keep the instance out of rotation until it stabilizes, rather than flapping it in and out of service. Similarly, firewall rules should be structured so that allowed traffic remains allowed even during scale events, instead of relying on brittle exceptions that might not apply to new instances. Timing awareness is part of making automation reliable because automation amplifies both success and failure patterns. Reliable automation also depends on observability, and these networking components play a big role in whether you can see what's going on. When a deployment fails, you need to know whether the failure was due to routing, load balancing behavior, or firewall policy, and that requires clear signals. If firewall rules are too broad or too opaque, you may not know what was blocked. If load balancer health is not meaningful, you may not know whether instances are truly ready or merely responsive. If routing is inconsistent, you may not know which path traffic took, which makes it hard to interpret symptoms. The automation-friendly posture is to configure these components so they support diagnosis as well as enforcement, because diagnosis is part of reliability. Beginners often focus on making it work and then forget that they also need to be able to tell why it works. In operations, the ability to explain a system is closely tied to the ability to keep it stable, because unexplained behavior tends to become repeated incidents. The security angle also becomes clearer when you view these components as enforcing different layers of a consistent model. Routers define connectivity boundaries and the intended network shape. Load balancers define service exposure and instance admission, and firewalls define which flows are permitted. Together, they create defense in depth while also shaping reliability, because they prevent unintended traffic from becoming unintended load or unintended access. Automation-friendly configuration aims to make these layers align so that security controls don't accidentally block healthy operations and operational paths don't accidentally bypass security intent. This alignment is not achieved by making everything permissive. It is achieved by being explicit about workload roles and dependency flows. When that role and flow model is consistent, automated provisioning becomes safer because new instances inherit correct network behavior by design. It also makes incident response calmer because you can reason about what should be allowed and what should be impossible. In other words, security and reliability support each other when the network is configured with coherent intent. As we bring this together, notice the common thread. Reliable automation depends on predictable paths, predictable service presentation, and predictable enforcement. Routers provide predictable paths when routing patterns match subnet intent and remain stable across environments. Load balancers provide predictable service presentation when health, readiness, and transitions are configured to match how services actually behave during startup, scaling, and replacement. Firewalls provide predictable enforcement when allowed flows reflect real dependencies and are applied consistently without accidental rule conflicts. When any one of these is misaligned, automation tends to expose the misalignment quickly because automated systems are relentless about repeating the same actions and expecting the same results. That relentlessness is a gift if your network is designed well, because it produces steady, repeatable outcomes. It becomes a headache only when the network foundation is inconsistent, because then the same automation produces inconsistent results. A network that supports reliable automation is one where changes can be introduced safely, traffic can be reasoned about clearly, and security controls reinforce rather than undermine operational stability.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.